This is the ELEC 1510 Logic Design Lecture 2 Video 2 on signed binary numbers, which corresponds to the textbook section 1.6. Now, I will say from experience that this is a very difficult topic for most students, and a lot of students struggle with this. So I would recommend that you watch this video several times, read this section of the textbook, and make sure that you really understand what's going on, because this is a pretty confusing topic. Let's just review 4-bit binary values. These are what we would call unsigned binary values. So I'm just going to write unsigned. So when we talk about negative numbers, or negative and positive, that means signed numbers. When we're just talking about positive numbers, that means unsigned numbers. That'll become more important in embedded systems design. The number 0001 in binary is the number 1 in decimal, or base 10. 0101 is going to be 5 in decimal. 0111 is going to be 7 in decimal. 1001 is going to be 9 in decimal. 1101 is going to be 13 in decimal. 1111 is going to be 15 in decimal. So I haven't here exhausted all of the possibilities of 4-bit binary numbers, but hopefully this is enough that you can, fill in the rest of the values for yourself. With 4-bit numbers, we can represent the positive numbers 0 through 15. Okay, so what happens though if we want to represent negative numbers? I mean, things like sine waves stay positive for a while and then go negative for a while and then go back to positive. There's a lot of reasons why you would want to represent negative numbers. Positive numbers are, only half of the numbers that are important. So we really have to represent them. In traditional binary numbers, if you just add up powers of 2 forever, it's always positive. You can only get 0 to infinity if you have an infinite number of bits. So we have to come up with ways to represent negative numbers using the same bits, but just a different interpretation of them. There are 3 main ways that negative numbers are represented, and only one of these 3 is really ever used. There's Sine Magnitude format, 1's complement, and 2's complement format, and 2's complement is going to generally be the one that's always used. It's the least straightforward of all of the methods, but it's the most often used. So Sine Magnitude format for negative numbers is where the most significant bit of the number is a sign bit. So that means that it can either tell you that the number is positive or negative. It tells you the sign of the number. So a 1 for the most significant bit means that the number is negative, and a 0 for the most significant bit means that the number is positive. So let's take 0001 for example. Well, the most significant bit is a 0, so that tells us it's positive, and the remaining bits are 001, so that's positive 1 in base 10. 0101 has, again, 0 as the most significant bit, so that's positive, and the remaining bits are 101, which is 5, so that's positive 5. 0111 again has 0 for the most significant bit, telling us that it's positive, so 7 is the most significant number that you can represent there. 1001, by contrast, has a 1 as the most significant bit, so that tells us it's negative, and then 001 for the remaining bits is 1, so this is a negative 1 in decimal. 1101 has a 1 as the sign bit, and then the remaining 3 bits are 101, so that's negative 5. And then 1111 is negative 7 in base 10. One of the things that's not very convenient about Sine Magnitude format is that 0000 is going to be positive 0, and 1000 is going to be negative 0. Now, there's no need whatsoever to have both a positive and a negative 0. This is just redundant. So we're wasting one of these representations. It wouldn't ever be used. So this isn't the most efficient way to represent sine numbers, it turns out. Another problem with this is that if we look at sine magnitude operations, let's add 0, 1, 0, 1 and 1, 0, 1, 1 together. This would be adding positive 5 and negative 3. So if we add these together, 1 plus 1 is 0 with a carried 1. Then again, 0 with a carried 1, 0 with a carried 1, and 0 with a carried 1. Now, depending on how you want to interpret this, you can either interpret it as a 4-bit number, in which case you would get 0, which is wrong, or you could interpret it as a 5-bit number, in which case you would get negative 0, which is also wrong. So sine magnitude operations, addition and subtraction, don't work. This is a representation for negative numbers, but it doesn't allow for operations to work. Okay, so then another representation is one's complement format. One's complement means that you subtract the negative number from 1 in order to get its binary representation, and 1 is 0001 in a 4-bit system. This also allows for positive numbers to start with 0 and negative numbers to start with 1. So again, there's a sign bit. Negative starts with 1. Basically, the simple way to take the ones complement of a number is to flip all of the bits, and then you change the sign. So if you had the number 1, 0, 0, 0, 1, then you just flip all of the bits. This was 1, positive 1. You flip all the bits, 1, 1, 1, 0, and that is negative 1. Now, it still has a 1 in the most significant bits place, which tells you that it's negative, and the positive version had a 0 in the most significant bits place. You just don't directly convert the remaining bits back into the magnitude like you did with sine magnitude format. So now, if you have a number that starts with 1 and you want to figure out what number that is, you have to flip all of the bits to determine the magnitude. Now, we'll do a few examples of that in a second. Let's look at 0001. Since that starts with a 0, it's positive, and so then we know that it's positive 1 in base 10. 0101 again starts with a 0, so it's 5 in base 10. 0111 again is 7 in base 10. 1001 starts with a 1, so it's a negative number. Now, in order to figure out what the magnitude of this number is, we have to flip all of the bits. So if we flip all of the bits of this, that's going to be 0110, which is 6. So that's negative 6 in base 10. 1101 starts with a 1, so again we know that it's negative. We have to flip all of the bits. 0010, which is a 2, so the magnitude is 2 and it's negative, so that's negative 2 in base 10. 1111 again starts with a 1, so we know that it's negative. Flip all of the bits and we get 0000, so that is negative 0. So unfortunately, again, we have 0000 being positive 0 and 1111 being negative 0. So it's not the same representation for negative 0 that it was in sine magnitude, but we still have an extra 0 that's redundant, just with a different representation. So this is not, again, a terribly efficient way to represent negative numbers. Let's look at a ones complement operation. So let's say that we add 0101, which is 5, to 1011, which is going to be, well, we know that it's negative because the leading number is a 1. Then we flip all the bits to get 0100, and that is negative 4. So this is going to be 5 plus negative 4. Okay, so 1 plus 1 is 0. Oops. 0 with a carried 1. 1 plus 1 is 0 with a carried 1. Again, 0 with a carried 1, and 0 with a carried 1. And now for ones complement operations, what you have to do is take the leading bit, the bit that you get that's more significant than the bits in either of the two numbers that you were adding together, and add it back to the end. So then we get 0, 0, 0, 1. And that is the binary representation for positive 1, which is the answer. So ones complement operations do work. Again, it's not terribly efficient because of the fact that we have a positive and a negative 0. All right, so now the most important negative number format is 2's complement. This is where you subtract a number from 2, which is 1, 0, in order to get its negative representation. Again, positive numbers start with 0, negative numbers start with 1 in this. So if you have a negative number and you need to figure out what the magnitude of that negative number is, you flip all of the bits, and then you add 1 to change the sign. So in 1's complement, we just flipped all of the bits. In 2's complement, you flip all of the bits and add 1. So if a number starts with 1, you flip all of the bits and add 1 to determine the magnitude. So 0, 0, 0, 1 is again a positive number, so its magnitude is 1 base 10. A typical mistake that all students make is when I say that this is a 2's complement number, what number is it? They will flip all of the bits and add 1, which if I flip all of the bits and add 1, that is going to be 1, 1, 1, 1, and then they'll tell me that that's 15, which is wrong because you don't flip all of the bits and add 1 unless it started with a 1, and it started with a 0, so we don't have to do that. These remaining 2 also start with zeros, so they are positive numbers. 1, 0, 0, 1, for example, starts with a 1, so we know that it's negative. And in order to determine the magnitude of this negative number, we have to flip all of the bits and add 1. So if we flip all of the bits, first we get 0, 1, 1, 0, and then add 1, and we get 0, 1, 1, 1. So that's going to be negative 7 base 10, because 0, 1, 1, 1 was 7, and the leading 1 told us that it was positive. I'm sorry, negative. So 1, 1, 0, 1 there. We have a leading 1, so it's a negative number. We first have to flip all of the bits, 0, 0, 1, 0, and then add 1, 0, 0, 1, 1. This is 3, and then we knew that it was negative, so that's negative 3 in decimal. 1, 1, 1, 1, again is negative because of the leading 1, so we flip all of the bits, 0, 0, 0, 0, and then add 1, 0, 0, 0, 1. And so that is the representation for negative 1. So what's convenient about 2's complement format for negative numbers is that there's no negative 0. So we can actually represent one more number in 2's complement than we could in 1's complement. So that's very convenient for us. So let's do a 2's complement operation example. Let's add 0, 1, 0, 1, which again is positive 5, to 1, 0, 1, 1. So we have to figure out what that is before we can know if the answer is going to be correct or not. And 1, 0, 1, 1, we have to first flip all of the bits, 0, 1, 0, 0, and add 1. So 0, 1, 0, 1. So this actually is negative 5. So if we add these together, the answer should be 0. Okay, so first we add 1 plus 1, and we get 0 with a carried 1. Again, 0 with a carried 1, 0 with a carried 1, and 0 with a carried 1. Now in 2's complement, unlike 1's complement, you don't use that 5th bit for anything. Or say if it was an 8-bit system, the 9th bit. Whatever this extra bit is that you get out in front of the answer, you don't use it. So 0 is the correct answer here.